Our last example is an audio predictor. In this case, we are going to use the mean squared error as a minimization criteria for the loss function. In this case, this does not differ from the target of the closed form formulation, and hence we obtain almost the same solution. Here, the desired target signal y is the audio input signal x, but one sample in the future. So what we can do is, for example, we remove the last samples of our audio signal as an input, and then the target would be our audio signal, but we remove the first sample for the signal to predict one sample in the future. So we import our Python libraries. We use again our vector to pytorch. We define here the filter length equals to 12. Here we will have a convolution in one dimension. It's a very simple one, so we have one input channel, one output channel, kernel size equals to L, which is defined as 12, stride equals 1, dilatation is also equals to 1, defined here, and here we have the padding, that will be dilatation times the kernel minus 1. So what we do, we will import our audio file, and in this case is a rock and roll legend from AC/DC, Back in Black. We will normalize. We will only train, just to make it faster, we will shorten this audio, and we will train just this amount of samples. So here we are plotting our audio signal, the shortened version, and here we can listen to it. So this will be our input signal that we're going to use for training. Here we're generating our model with the mean squared error loss function. Again, we use the Adam optimizer. We then train our model. We save the weights. And now we will process, after training, we will process the full audio signal. So it's not the shortened version, but we use the full audio, and we will make predictions based on the obtained weights that were trained on the short audio. And this is what we are doing here. Here we are plotting the original and the prediction. So we see it here. And the prediction error. And here also we see the weights, and we can listen to the predictions. So this is a very, very basic and simple linear predictor that we're predicting one sample in the future. To finalize this tutorial, I leave you an exercise, and this exercise is to design a sampling rate up converter for an audio signal sampled at 8 kHz to a sampling rate of 32 kHz. For the training, we will generate the 8 kHz version by using a low-pass filtering and downsampling a 32 kHz version. So you can have, for example, audio samples taken from freesound.org. So the task is to design the low-pass filter as described, for example, in ADSP tutorial part 8, and also upsample it using this filter. So listen to the upsampled result and see if there is some audible artifacts, if there is not enough stop band attenuation. Then you can use a convolutional neural network to interpolate the missing samples, and you can use an autoencoder and decoder structure that it's present on the next set of slides, and then you will train it on audio signals 8 kilohertz sample version as the input and 32 kilohertz original as target. So on the next tutorials we'll talk about autoencoders, and you can then try this exercise. Then we'll just compare the result with the traditional upsampler using the low pass filter and try to obtain better sound results using neural networks. So this is an exercise that you can start thinking about it now, and by the end of this tutorial you can try it out. And here you can find a link to the tutorial on filters from Advanced Digital Signal Processing Part 8, and here the GitHub with Jupyter notebooks and interactive examples. So that's it for today, and see you next time.